，V 角为角，因为就是并在一起，是把银行对论是把 GR 是放下去，这个 QM 是
Okay, so we have to start, otherwise we'll run out of time.
Yeah, sure.
Okay, so for this question, it's somewhat by definition. So this one by gamma A, this one.
它的意思是 Y，
And then
是每天这个gamma是第四个。
So basically we just use the definition, and then what we do is we put it into the F D alpha, and we just use product rule. So the product rule, let's run. So the product rule is gamma F G alpha plus F gamma B alpha. By the way, can people on the Zoom hear me? Okay. Doesn't really matter. Well, I think Min, I think Mayan is on the Zoom, right? Yeah. Basically, after you do this, you just do it a second time. So you take, but we have to be careful because this becomes kind of a tensor object. So because this has a lower index gamma and it has an upper index alpha. So what you have to do is you have to make it be alpha gamma. And then you have to change the definition for the covariant derivative. Remember for that? Yes. It's just a new tensor. It's just something I define because this one has a upper index gamma and this one upper index alpha and this one has a lower index gamma. So I just redefine this. It's easier for you to see the next step because when you take covariant derivatives of vectors, it's like this. But if you take covariant derivatives of tensors, it becomes a little different. There's one extra term. Okay. So if you take the covariant derivative of tensors, you get this one beta of B alpha gamma, and then you get partial beta, big B alpha gamma. And then you get kind of the same thing here, gamma, and then you have an alpha on top. And you have, B. B. Then you take the index on the gamma. So you take gamma and then you put any other Greek symbol, let's say nu, or let's use rho. Actually, let's use rho. So rho, and you put rho up here. And then you have a beta. Then you, is that right? No, that's not right. Sorry. This should be beta. And this should be gamma. So then you subtract alpha, gamma, rho. B, this should be rho as well. And this should be beta. So this is the new definition of because when you take covariant derivative of tensors, it's a little bit different. You have to add this additional term because you have two indices. So what you do next is you substitute this definition inside. So you see this one, this blue, this one into here. So what you do is you take so this one is a partial derivative. So, well, let's see. Before we do this step, maybe we should do one more step before we, before we do this step, let's do something before that. So let's move this. We need this, but we'll move it down a little bit. So, what's the best way we can do this? Let's take the partial derivative. No. Actually, don't do it this way. Don't do it this way. Let's just take the second derivative like this. So we take partial beta, partial gamma, and F of V alpha. And then we use product rule again. So this way will be a little bit faster. So beta V alpha gamma F plus, and then V alpha beta partial gamma F. And then we add the other one, partial what is this? Beta f partial gamma v alpha, and then you add the last term. Partial beta partial gamma. Yeah. Is this clear right now? Because you take two covariant derivatives. But then the definition is a little bit hard. So remember, if you have scalar functions, so if you have a function like this, partial derivatives. So partial derivatives become covariant derivatives become partial derivatives. So v beta becomes partial beta. And then if you take the anti-commutator, so basically you do this, because partial derivative partial beta partial gamma is equal to partial gamma partial beta. So this one cancels, right? Because this becomes a partial derivative if it's just a function, right? It's not a covariant derivative anymore. So the only terms that remain are the other terms. So it will be this one. Right? Oh, someone's text. Let's see. Okay. So what can we do now? This is the tricky part. It's because when we take second covariant derivatives, it's not so easy because this becomes a tensor of rank 2. So this becomes something like, as I mentioned before, B alpha gamma. So the definition changes a little bit, but here some things become somewhat simple. So let's scroll down. Give me 1 second. Sorry. So what happens is, let me just check if this expression is correct, because I'm not super confident in mine. Okay. Okay. So what's also good? This is actually really simple. So, sorry, this is a little bit overcome. So do you guys get why this one vanishes? Because this one becomes a partial derivative. So beta and gamma become partial. And then when you just take the commutator, they vanish. Yeah. But notice these two terms as well. These two are this one and this one. So you see this term is very interesting. This one and this one. This one. They're the same, but with opposite. So they're the same term, but these two are swapped, right? The beta and gamma are swapped. But if you take the commutator, these two cancel each other out because you swap, because you subtract. So you're only left with this term, right? So it cancels out quite nicely. Do you see it? So because you swap the beta and gamma here, so this is like this. You're subtracting another term, but these two terms are actually the same thing, but with just the swap beta and gamma index. So these two actually also cancel. So what you're left with is something quite nice, is partial beta, this one of f v alpha is simply equal to f partial beta partial gamma v alpha, right? You get it? You get it, right? Do you understand, or so this one, you know why it cancels. This one becomes a partial derivative when it's only a function. So if it's partial can swap the index, and then they become, and then you subtract them, right? So they're the same. But this one is, you see these two terms are very similar. They're exactly the same. But if you take the commutator, these two are symmetric. So if you take the commutator, they cancel each other. Get it? So this is the only tricky part that we have to do. So this is the because this is the next step. What we have to do in the next step is to actually compute this term, and this is not very easy. So we do the partial gamma b alpha is equal to partial gamma b alpha is equal to this one, gamma b alpha plus gamma mu b mu, and I'm going to define this as a new tensor, alpha gamma, because this one has a lower index gamma and this one has a lower upper index alpha. So I'm just going to define it as a new tensor. Okay. So, and then we remember when you take a covariant derivative of tensors, as I said before, the definition is a little bit different. So you take partial beta, a alpha gamma is equal to partial beta, a alpha gamma plus partial this one, gamma beta. Let's define a new variable, sigma. We have sigma. This one has a sigma index, and this one has an a. So a sigma, and this one has a rho. Sorry, rho, and then we have a alpha. We have a gamma here, and we minus this one, alpha gamma rho, a rho, gamma. No, beta. So this is the new definition. So what we do is we substitute this expression, this one, into here. So you see this big one, we just substitute it into here. So we get this really ugly term. So partial beta gamma of v alpha is equal to this long one. So it will be partial beta, partial gamma, v alpha, plus v mu, partial beta, gamma alpha, gamma mu, plus we have gamma alpha, mu, partial beta, v mu. And then I've done this by taking the partial derivative of this whole thing. So I took the partial derivative of this. Basically, I just took the partial derivative of this. So by taking the partial derivative of this, I get an additional term. So I get this gamma alpha rho, and I put the definition of a rho here. So a rho, a alpha gamma is just this term. So I just plug it in. So I get partial gamma b sigma. Sorry, or v rho actually. Rho. Sorry. Plus this one, rho gamma mu, v mu, and we add another term. Subtract another term, sorry, because this one has a minus sign, so we have to subtract. So this is where you have to be a little bit smart, because some of the terms here are not really that trivial to see which one vanishes. So okay, if let's see, are all the index right? Yes, the indices are right. So if I take the commutator here, which term can we see immediately vanishes? So remember, partial derivatives always commute. So the first term must vanish, right? So if we commute them, some of them are, the next are kind of non-trivial. So you can see that the third term here and this one and which one? The third term and the sixth. Oh, sorry, there's a minus sign. Oops. So you can see the third term and the sixth term here, right? Are the same thing, but they just have an extra, they have the same dummy variable, dummy index. So they're exactly the same, but the dummy index is different. So dummy index is sigma, this is the dummy index is mu. So they actually cancel, right? Even without the commutator, actually, these cancel. So if these two cancel, this one, the rest, unfortunately, the next part is really non-trivial. It's this really ugly term that doesn't really cancel because well, it cancels, but it's really non-trivial. And when I gave you the problem, I didn't anticipate how hard it would be to show that this cancels. But in fact, this is symmetric. So if you change alpha, beta, and gamma, this will actually cancel. So I can show you how, but it's really, really hard to see. So remember the definition of the Christoffel symbol is this, a half T alpha lambda, partial lambda, partial beta, T rho lambda plus partial partial rho T beta lambda, and you subtract partial lambda T beta rho, right? So if you multiply this by this one, it doesn't seem to cancel trivially. It doesn't. Okay, so the point is, if we take the anti-commutator, we want to show that if you swap beta and gamma, this part is symmetric. So we want to show that this part cancels, but it doesn't actually cancel that trivially. But the trick is to do something somewhat clever. So you have to do partial beta, partial gamma, and then T rho u, like this. And I can see some people are really confused why you do this, because this is definitely symmetric if you swap beta and gamma, right? This one is definitely symmetric, but you will see something interesting. So if we take the chain rule, partial beta, partial gamma, T rho sigma lambda, and then oops. So this is a very, I think it's a really cool trick at least. So plus T rho gamma lambda, partial gamma T rho, like that, right? Is that right? So I just use product rule here. But the next step is to take the second derivative, partial beta B rho, partial gamma. So it seems that I'm doing something that is really stupid because I'm making it more complicated. But you will start to see why this is a cool trick. Do you see it now? Because this one is symmetric, and we want the target terms we want is this one and this one, right? Because this one and this one is exactly the same as the term that we want to show is symmetric. So it's exactly the same as this one. Exactly the same as this one. So these two terms, this one and this one, is exactly the same as the one before. But notice what I can do is subtract these two to get these two. And these three terms are symmetric, right? Do you get it? Because these three terms are symmetric. If we subtract this, we get the target term that we want. That means the target term is also symmetric. Is that confusing? Is that, or you can just, yeah. So the nice trick is, so this actually, if you non-trivially, if you take the commutator, this actually also cancels. And you can clearly see it will start to form the definition of the Riemann tensor, because this has a partial derivative here, and then it has well, maybe I shouldn't cancel the whole thing. I should cancel the part that I don't want. So I cancel this one. And then I don't, yeah, I'm not actually canceling the whole thing. So I cancel this one. So you see, the Riemann tensor has quadratic terms in gamma. So it's double gamma, and then partial gamma. And if you take the commutation, you'll get the Riemann tensor. Up here. Do you get it? Because you want to show that the other terms, when you take the partial derivatives, are symmetric. And then once you show they're symmetric, you keep the remaining terms that are not symmetric. That will keep the Riemann tensor. And the next question is quite nice. It's kind of a concept question. Maybe I can ask you guys what you think. So alpha, beta, gamma, delta. And then V delta. So what my first question is, sorry, delta. V alpha. So we see this term, right? So my first question is, what happens when V is a constant vector? So if V is a constant vector, this vanishes, right? This becomes 0. If this is 0, then what does that mean? So if this whole thing is 0, so either this is 0 or this is 0. But if this is 0, this is a trivial solution, right? This is a meaningless solution. So what does it mean for the Riemann tensor to be 0? It's just flat space-time. So basically, V can only be constant in flat space-time. And maybe I'll tell you later, but actually this is related to, the reason why this is cool is because this is why you cannot have supersymmetry in GR. So this is exactly the reason why you cannot have supersymmetry in GR. So maybe this is the question that you're more concerned about. He always asks you to compute Christoffel symbols. So the trick here I'm going to show you all is probably very valuable. It's called the Lagrangian trick. So if you have something here, a metric like this, so this is one of the quickest ways you can do to calculate the Christoffel symbols. So remember the geodesic equation. The geodesic equation is x dot dot mu plus right? That's the geodesic equation, right? So the trick is to convert this into a Lagrangian and then compare with the geodesic equation. So how you do this? You can just write anything like this as a Lagrangian. So you just convert dx alpha to x dot alpha, and then you use the Euler-Lagrange equations. So the Lagrangian is just minus t dot squared plus h, and then x dot I plus x dot j. And what you do is, if you guys remember from classical mechanics, the Euler-Lagrange equation is partial L partial x alpha minus dd lambda. So remember, in this case, we're not doing time because in GR, there's proper time and coordinate time. So here we have to use the affine parameter. So the affine parameter is basically t, lambda, and all the other parameters, x. So all the coordinates are dependent on lambda. So this is how you define. So it's basically when you do polar coordinates or something like that, you define it by one parameter, lambda, or some other coordinates you define by one parameter. Namely, in this case, you would do lambda. So partial L partial x dot alpha equals 0. So everybody's probably thinking, why do I bother doing this? It seems stupid, right? Because you have to remember the Euler-Lagrange equation. But I will tell you, if you manage to do this, you can not only get the geodesic equation, you can get every single Christoffel symbol in, depending on how many variables there are. So here there are only 2 variables, so you will get all the Christoffel symbols just by computing 2 Euler-Lagrange equations. So you don't have to input everything at once. So I'll do that for the t term. So let's do it for the t term. So for the t term, we take partial L, partial t, and here h is the only function of t. So partial L partial t is just h prime t. H prime x dot j I x dot j, right? Because this is the only function of t. And these are not functions of t. So these are just independent coordinates. So now what we do is we take partial L, partial t dot, right? So partial L partial t dot is just minus 2 t dot, right? But then I take another derivative from the Euler-Lagrange equation, right? Take another derivative. Oh, sorry, t dot. Then you just get minus 2 t double dot. And then you just plug it into the Euler-Lagrange equation. You get minus 2 t double dot is equal to h prime x dot, x dot I, x dot j. So t double dot is, so I'm going to write it in this way. And I'm going to write it up, so I'm going to write it down here. So t double dot plus h prime over 2 is equal to x dot I and x dot j. So why do I do this? If you compare to the Christoffel symbols, I mean the geodesic equation. You can see that this term here is precisely gamma t ij h prime. And remember, if these two index are different, I and j different, you have to divide by 2. Because this is symmetric, the Euler-Lagrange equation cannot determine the difference between ij and ji. So you always have to divide by 2 because this is exactly the same. So remember, if these 2 indices are different, you always have to divide by 2. Sorry. So that's the Tij term, right? And in general, this is easier because you don't have to remember the definition of the Christoffel symbols, at least in my opinion. Do you think it's easier to remember the definition or just compute it using the Euler-Lagrange equation?
You can, but he might say that you are not using these methods.
But the thing is, actually, this thing is derived from the Euler-Lagrange equation. You get it from the Euler-Lagrange equation. So actually, in the lecture notes, he wrote the Lagrangian method down, but he didn't tell you that he did.
Partial ones from
I'm sure you can.
Great from the exact exactly.
I'm sure you can get full.
Results,
I'm sure you can get full points because
I'm not sure.
the thing is, I think it's gonna be fine, right? Because it's essentially the same thing, right? I don't know what you guys think. I think it's exactly the same because oh shit, am I running out of time already?
No, it's just a
Tell us.
question mark.
Okay. So now what you need to do is you need to compute all of them. So you just do the same procedure as the x part. So you take partial L, partial x, and what is that? There's no x term here in this because none of them are dependent on x, right? So this is just 0. So this is quite nice. You do partial L, xi, partial L, partial xi, xi dot, sorry. So what do you get? So this will be partial L partial x I dot is just h x j dot, right? And then you take another derivative. Partial L partial xi dot, and then you d lambda, right? So you take the derivative, so you take the partial derivative with respect to h, so this is just h prime, and then this will be t dot plus, and then it will be xi double dot, right? By chain rule, by product rule. So this is double dot, and it's just prime and then t dot. So what's nice about this is exactly equal to 0. So the term that you want is, so this will be gamma j t j is equal to a half h prime, right? Is that right? Yes. Or did I miss something? Yeah, that should be right. So, and then the reason why we're doing it like this, we then use the definition of the Riemann tensor. So the Riemann tensor Tt is equal to partial alpha Tt minus partial T T alpha plus gamma alpha beta Tt. But what's nice about this method is now you have all the Christoffel symbols quickly, and you know that the first term cancels because in the x equation, so basically if this is x, there's no double t component, it's just t and j. So this one must cancel. So the third term also cancels because there's no double t component. So the RTT component is quite nice. And then minus shoot, is that a t? And now you know what all these components are, right? So you know this one, this one, and this one based on what we got just now. So you know that TJT is just, so this is just minus partial t of wait, am I missing? Wait, am I missing something? Partial t is partial t. Yeah, that should be fine. So now we take the partial derivative of this, and we get right, and then we take subtract the mixed t term. So this will be, wait, where's this? Oh, we need this term. So gamma t. So this will be sorry, this should be this should be just h prime and the h prime. It's a quarter. Should be right. So this would be minus a half h double prime. Like that. So the point is to use the Euler-Lagrange equation because it's easier to compute the Christoffel symbols, and then you sub it into the definition of RTT. Right? You look confused. What happened? You look confused. Is there anything wrong?
Is that RTT basic? Because usually Riemann curvature tensor for
yes, but you RTT is just RT alpha t. So you can contract the
Oh, so like
person.
the same one is.
Yeah, not really cancel it out, but it's just this definition on top. And then you just make alpha and gamma the same. And then you sum over every single alpha and gamma. I realize there's something wrong in my solution, so. Wait, I think I know what's wrong. Ah, I see what's wrong. Okay. Wait a minute. Ah, okay, I know what's wrong. I forgot to multiply this by h. So that's why. Okay, that's why I got it wrong, because I thought, okay, so this should be, so we divide all sides by h. So it'd be h bar over h, h dot over h. Okay, so that makes more sense, because now I see why it's not so correct. Okay, then this makes more sense. Because actually, I was really confused why I was wrong, because the thing is, you should be able to get Friedmann's equation from this equation. So the cosmology equation from this equation. You know, the one that Dr. Lee derived in the class for the Friedmann equation. So you should be able to get it from this. Okay, so that's why it's wrong. Okay. Right? So this is h double dot h minus h dot squared over h squared minus double dot, right? And this should be a quarter. So then you get h double dot over h minus h dot squared over h squared minus a quarter h dot over h all squared. And then you get something like h double dot h minus, is that right? Minus minus. Okay, so this should be minus and this should be plus. So this should be, my math is terrible today. 3 over 4. So that's basically the Friedmann equation, right? So you get 1. This is the whole parameter double dot over h. Now h dot squared over h squared. So this is the gist of the question. So basically, the reason why I asked you to, well, I didn't ask you, but the reason why I chose to do this is because this equation gives you the Friedmann equation for free, because this is just the FLR W metric that you learned in class. So it's the most general form. So if you want this in polar coordinate or spherical coordinates, you just change this to the spherical thing. And then if you want it in Cartesian coordinates, you just write it as the Cartesian coordinates. So here, you get the Friedmann equations for free using the Euler-Lagrange method. And if you want to use the actual definition, I urge you not to do so, because if you think about it, you have to use this definition here many times, right? So if you have to change every single index every time. So it's very slow. That's my point. So maybe I'm saying it not nicely, but the way that they normally teach you how to do it is extremely slow. So by doing it using the Euler-Lagrange method, you get all the Christoffel symbols in one go, at least every single one using. So let's say here, right? If you have 4 indices each, you need